Hello, and welcome to Poker Hands and Probability. This is a bonus video for Finite Math, specifically talking about cards. My name's Tuesday J. Johnson. I'm a lecturer at the University of Texas El Paso and an assistant professor at Doña Ana Community College. So a poker hand in general consists of 5 cards chosen from a standard deck of 52 playing cards. When you're dealt a poker hand, you're looking for all sets of 5 cards chosen from the deck of 52. So the number in our sample space, overall, just any card from a poker hand, will be the number of combinations having 52 cards and wanting 5. Using our combinations formula, that's 52 factorial divided by 5 factorial times 52 minus 5 factorial. And whether you do it by hand or you use your calculator, you will end up with 2,598,960 different combinations. Now we're going to look at a couple of specific combinations in these poker hands, and the first one is a full house. A full house is the set of 5 cards chosen from a deck of 52 with particular things happening here. 3 are of one denomination, and 2 are from another denomination. So we might have ace, 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 and then king, king. And 3 of one denomination, value, and 2 of another. So as we saw on this last slide, the sample space is the set of all 5 card sets from a group of 52, which is our 2,598,960. This will be our denominator as we're trying to find the probability. That's the side, that's how many of all 5 card hands we could put together. So now let's detail the full house. Remember, that's 3 of one denomination, 2 of another. So we're going to choose the first denomination. Out of the 13 different suits, ace, 2 through 10, jack, queen, king, there are 13 suits. We want one of those. And from that suit, there are 4 cards. There's clubs, spades, diamonds, and hearts. So 4 different suits. We want 3 of those. All right, 3 cards of the same value. And then we'll choose our second denomination. So we've already chosen one, maybe our aces as I wrote on the last slide. There are 12 left, 2 through 10, jack, queen, king. And 2 cards of that value, C of 4 times 2. Now this is a decision algorithm. It's a decision algorithm in which we're using the multiplication principle, or it's a sequence of choices. We choose the suit, we choose 3 cards, choose the next suit, choose 2 cards. We end up with 3,744 different ways that we can get a full house. 3,744 different ways out of 2,598,960 different 5-card hands. Your chance of being dealt a full house is less than 1%. It's just over 1/10 of 1%. So not very likely, but you know, you get there eventually. 2 of a kind. This is 2 cards of a single denomination and 3 cards with other denominations. They're different from each other and from the pair. So you only have 2 cards that have the same value. All the other ones are different. So the probability of being dealt 2 of a kind. Our denominator is still our 2,598,960 ways of being dealt any 5-card hand from a standard deck of 52. But now, because I want 2 of a kind, also known as a pair, out of the 13 denominations, I choose one of them. And out of the 4 cards of that denomination, I want 2 of them. This is my pair. And then, so a sequence of choices, our next step is then, out of the 12 denominations left, I want 3 of them. Right? Maybe I want a 6, a 9, and a queen. And from each of those suits, I want only 1 card. They have 4 in each suit. I choose 1. So I'll have 13, choose 1. The combinations of 4 things taken 2 at a time, and so on, to get 1,098,240. You can see that this probability is a lot closer to a half. So it's not surprising that you can be dealt a pair. That's why a lot of times in games, you have to have jacks or better, because anybody can get a pair of 3s, but you got to have something worthwhile before you start betting in a lot of games. 3 of a kind. This is 3 cards of the same denomination, 2 cards that are different from each other and different from the 3-card combination. So we still have our denominator. This will always be our denominator. That's all possible 5-card hands dealt from a deck of 52. 3 cards of one denomination. So out of the 13 denominations, I choose one of them. For the 4 cards of that denomination, I want 3 of them. Now, I need 5 more cards. I need a total of 5 cards. I need 2 more cards. So the combinations of the other 12 denominations, I want 2 of them. Remember, the other 2 cards have to be different from each other and different from the originals. So once I have those 2 denominations, 4 cards in one denomination, I want 1 of them. 4 cards in the other denomination, I want 1 of them. Here we see I have 3, 4, 5 cards total, and I have 1, 2, 3 different denominations. 3 of the cards all the same value, maybe 3 aces. And then I have a 7 and a 4, perhaps. 54,912 different options, which is about 2%. 2% of the time you'll be dealt 3 of a kind on the opening deal. 2 pairs. That'll be 2 cards of one denomination, 2 cards with a different denomination, and 1 card that is yet different from the others. So maybe I have a pair of aces, a pair of kings, and then a queen on the side. The number of ways we can be dealt 2 pairs is given by. So when we first start out, there are 13 different denominations. And I want 2 of them because those are going to be my pairs. Now, from the first denomination, there are 4 cards. I want 2 of them. From the second denomination, there are 4 cards. I want 2 of them. All right, so you want 2 of each of those from the 4 of that denomination. Now, we've eliminated all of the aces, all of the kings. Out of 52 cards that we started with, we're now left with 44. Out of those 44 cards, I need 1 more to complete my hand of 5. All right, 2 denominations. I have a pair in one denomination, a pair in the other one. I have 4 cards in my hand now. Out of the 44 cards left in the deck, only 1 of them is what I need. I end up with 123,552 possible ways that we can be dealt 2 pairs. And the probability is then the probability of the favorable outcomes, 123,552, divided by the probability of the sample space, 2,598,960, which will give us about 4.75%. So, 1 out of 20 times, you're going to be dealt 2 pairs if you play poker enough. Alright, so our last problem here, lucky 2. This comes to me from a student at the University of Portland. Shout out to Muhammad and his classmates. This was on one of their exams, so it's a great question to look at. So, lucky 2. You were dealt a hand with 2 pairs of matching cards that has either 2 jacks or 2 aces, but not both. How many different lucky 2 hands are possible? Now, we saw on the last slide, there's 123,552 different ways to be dealt 2 pair. But this is different. It's more specific. So let's count the ways. Let's suppose we're dealt a pair of jacks, but not aces, right? Either 2 jacks or 2 aces, but not both. You have 2 pairs. So we take 1 suit, jacks, and we want that 1. And from that 1, we want a pair. Now, we took jacks, so we cannot have aces. That leaves 11 denominations remaining. And we want 1 of those denominations from which we get a pair. So now we have a pair of maybe 10s, and we have a pair of jacks. There are 44 cards left, because we could have an ace on the side. The ace just can't be in a pair. And it turns out that what I've typed here is absolutely incorrect. When we multiply this is 17,424. It's a comma here in the US. So 17,424 different ways we could get a pair of jacks and another pair that's not aces. But it doesn't matter if it was jacks or aces and then not jacks. It doesn't matter. It's the same result, same possibilities. We leave out 1 suit. So this was the assumption that we had jacks but not aces. If we double it, we'll have aces and not jacks. Therefore, doubled, we have 34,848 different ways to be dealt lucky 2. And we can find some probabilities with that, but not today. Thanks for listening.